You did a little bit of this in advanced functions where you worked on writing the equation of tangent lines to curves. So we're going to do this with calculus, just showing you that you don't have to memorize the slope expressions for these particular things, nor do you have to do the instantaneous rate of change at a particular place in order to do it. What you're actually doing when you do an instantaneous rate of change, of course, is taking a derivative. So we're just going to skip the numerical part and go straight to the function analysis. So the first one we're going to do is the function f of x is 4 over 3x minus 2 plus 5. And I want to find the tangent, or find the line that is tangent, and the equation of the line that is tangent to f of x when x is 1. So first thing I'm going to do is write this function in negative exponent notation, like so. Okay, so when you go to write the equation of a line, there are two pieces of information you need to have. You need to have the slope, that's there, and you need to have the y-intercept, that's there. So I can get the slope by taking the derivative of this function, because that's what derivatives do. So I'm going to take this thing and I'm going to do its derivative, df by dx, leave the 4 alone, negative 1 comes in front, 3 to the x minus 2 to the negative 2. I have to do the derivative of the inside here now. So the derivative of 3x to the negative 2, the 3 stays alone. The derivative of x to the minus 2 is 1. So I have that. And the derivative of a 5 is gone. So if I were to clean this up a little bit, I end up with df dx equals 4 times 3 negative, and there's a 3x minus 2 in the denominator because it's negative and it's squared. Alright, so negative 4. This 3 cancels one of the 3's that are down there, and I end up with this as my derivative. Okay, so I have an expression for the derivative of f. I just need to find out what the value of that derivative is when x equals 1. So the derivative evaluated at x equals 1, that's how you write that, is negative 4 over 3 times 1 subtract 2 squared, which gives me negative 4, 3. 1 minus 2 is negative 1, and negative 1 squared is 1, so my slope would be negative 4 thirds. Alright, so I can plunk that into this equation. Y equals negative 4 thirds of x plus b. Okay, so to get my y-intercept, I need to fill in an x value, which I have, and a y value, which I can get from the function. So I'm going to get that y value by substituting in 1 for x, before, I'm just going to use this version, 3 over 1 minus 2 plus 5. 1 minus 2 is negative 1. Negative 1 times 3 is negative 3, so I end up with negative 4 thirds, and 5 would be 15 thirds, giving me a total of 11 thirds. Alright, so 11 thirds is equal to negative 4 thirds when x is 1 plus b. Kick that over. 11 thirds plus 4 thirds would be b. 11 and 4 would be 15 thirds, and 15 divided by 3 is 5. Therefore, the equation of the line that is tangent to this function when x equals 1 is y equals negative 4/3 x plus 5. So if I were to make a little space here so that I can pop a picture of this function up for you. Let's see. Give me a drum roll. I'm going to put a sketch of this with the tangent on it. So there's the sketch, and there's the sketch with the tangent on it, and you can see that indeed it does work out. So let's try another one. Okay, so we're going to give a sine function a try. So the fact that I've changed the base function doesn't change the process. I still need to have a slope and a y-intercept. I'm going to get that slope by finding the derivative of this thing and then plugging in the x value that I'm after. So dg dx is going to equal, derivative of a sine is a cos, so 2 cos 3 times x plus pi over 4. Derivative of negative 1 goes away. This is a chain rule, so I have to finish with the derivative of 3x plus pi over 4, which is just 3. So my derivative is 2 times 3 is 6 cos 3x plus pi over 4. So that derivative then, if I were to evaluate it at this particular x value, dg dx, evaluated when x is pi over 12, would equal 6 cos of 3 pi over 12 plus pi over 4. Just a little quick sketch work here, plus pi over 12. Pi over 4 is 3 pi's over 12. That would be 4 pi over 12. And 4 pi over 12 is pi over 3. So dg dx at x equals pi over 12 would be 6 cosine of 3 pi over 3 3 times pi over 3 is just pi. Cosine at pi is negative 1, so my value for the slope is negative 6. Okay, so far I have my tangent y equals mx plus b, has a slope of negative 6 when x is pi over 12. I don't know my y-intercept, I don't have a y value yet. So I'm going to plunk my pi over 12 up into here. So g at pi over 12 equals 2 sine of, now I already worked out that pi over 12 plus pi over 4 times 3 gave me pi. That's what that's worth. Sine of pi is 0. 2 times 0 is 0. 0 minus 1 is negative 1. Alright, so if the y value is negative 1, 6 times pi over 12 would be negative 6 pi over 12, which is the same as negative pi over 2. Kick this over. B is pi over 2, subtract 1. So the equation of my tangent then is negative 6 for the slope. So I got that from my derivative. And plus pi over 2 minus 1 as my y-intercept. So if I go through then, and just like before, I make a little space so that I can show you the actual graphs and the tangent to confirm that I've done my work correctly. Alright, so here's the graph of the function, and here's the function with the tangent on it. And you can see that that function does indeed have a tangent at that place that looks just like that. Okay, So we'll try this on a composite. We'll only do one of these because the process is exactly the same as for a basic function. I need to get my slope and my y-intercept from this particular function. So I'm going to take the derivative to get my slope. dm by dx will be, the derivative of a ln is 1 over the argument, so x4 minus 2x squared plus 1. But I'm going to need to do chain rule because I have a non-simple argument there. So the derivative of x4 minus 2x squared would be 4x cubed minus 4x, which gives me a first derivative of, well, I can factor 4 and an x out of this, leaving me with an x squared and a minus 1 up here. And that thing in the bottom, that will factor as x squared minus 1 squared. Lovely. Which simplifies, one of these divides out one of those and leaves me with 4x over x squared minus 1. Okay. So in order to get my slope, I need to evaluate that derivative at x equals 5, which would be 4 times 5 over 25 minus 1. 5 squared is 25. That gives me 20 divided by 24, which is the same as 10/12, which is the same as 5/6, which is approximately 0.8333 repeated. So instead of using the 0.8333 repeated, I'm going to stick with this 5/6. So far in my equation, y equals mx plus b, I have that the slope is 5/6. I have an x value already of 5. I do not have the y-intercept. If I could get a y value at 5, then I would be able to plunk it in here. So the function evaluated at 5 will give me my y value. It's ln of 5 to the power 4. 5 times 5 is 25, times 5 is 125, times 5 is 625, minus 2 times 25 plus 1. So m at 5 is the ln of 625 minus 50 would be 575, plus 1 would be 576. Okay. Now, I could evaluate that as a decimal, or I can just drop it in here in that form. This is just a number, so it can be used like any other number, so in it goes. Ln of 576 equals 5 times 5 would be 25/6 plus b. Kick this over, I get ln of 576. Subtract 25/6 is my y-intercept. So the line that is tangent to m when x equals 5 will be y equals 5/6 of x plus the ln of 576 subtract 25 over 6. Now that looks really gross, but 5/6 is a perfectly acceptable number for a slope. In fact, in grade 9, almost all of your slopes are fractions. And ln of 576 is just a number. So if I were to type that into Desmos, I should get this as my function. And if so that's this thing. If I were to put that in there, and if I were to add this line to it using ln 576 and this thing as the y-intercept, then I will get a tangent that has no rounding errors like this. And so you can see that it does in fact just clip that function at one spot nicely. Okay, now as a bonus, you could take this function and you could actually do the sketch analysis on it. So if you look at it over there, it's pretty fun looking. You notice it has two vertical asymptotes. It has a maximum at 0, and it does not appear to have any points of inflection. So as some exam review, if you'd like, go through, try and sketch that one, doing all the analysis tools, so that you're good for the exam. Good luck.